Thank you, Larry. Yes, Larry and I shared a stage. The poor video guy was panning up and down constantly as we were standing there. Sorry, Larry. So as Larry said, my name's Troy Magennis. I run a company which consults and helps companies forecast and manage risk. Very boring. I love the smell of math in the morning. Thank you for being here. It's not going to be too heavy. It's a 40-minute talk, and I want to draw your attention to, if you don't have to take notes, you can all get the slides, you can all get some of the software I use in here. If you go to bit.ly/agilesim, you can download them. So you can pay attention to my talk without having to worry about taking notes. So forecasts are about answering or speculating about the outcome of events which haven't occurred yet. Some of those being the ever-present one, when will it be done? How much, how many staff are we going to need? How much is it going to cost? And one which I think we don't use enough, cost of delay. And what we're doing when we're forecasting is we're speculating about an outcome. Now, the problem that enters into the equation is that when we go on record with a single value result, and that's not what actually happens in the real world. There are so many uncertain inputs which make up these forecasts. There's a range of results, and where we often get into trouble is that we default to giving an average, or we default to giving one value. Someone grabs that, they double it. Someone grabs that, they double that again, and soon enough we don't have a funded project and we look stupid as IT. So that's the first key takeaway, and if you get nothing else, this is the key point. When you forecast, there is no single result. It's not possible. Even the fact that we give an answer, a forecast to someone, changes their behaviour, altering the outcome of what the project's going to be. When we look like being late, more staff are added. That's going to change the original forecast. So when I talk about forecasting, it's about the ongoing management, understanding how we present uncertain numbers to our executive peers. And we do that in a way which runs the conversation in the direction we want it to be, which is trying to maximise the company's earnings and cash flow. So this talk specifically looks at an easy way that Kanban lean practitioners can actually do today. Cycle time forecasting uses the historical values of cycle time, which is a very easy to capture metric. You trip over it in Lean and Kanban. It's the date that your cards entered the board and the date that your card fell off the board into production. Even if you just have those two dates, you can actually calculate a series of cycle time samples that you can use to forecast the future. So cycle time has a lot of advantages. It's also very difficult to game. If you do use the outer lead time, it's much harder for someone to, how do you make a project in jeopardy using story points of velocity become on track? You just sort of change the number of story points and then the velocity changes, and all of a sudden it looks like it's on track again for another couple of months. Cycle time is very difficult to game as a metric, and it can be measured at many different levels. You can do it at the story level, the feature level, and you can use these different forecasts at different levels to cross-check your models to make sure that it hasn't been manipulated at one level or the other. So cycle time is a very robust tool for doing good forecasting of dates. If we have dates, we can work out a cost. If we have a date, we can work out the cost of being late. If we have cycle time for each individual section of our Kanban board, which may relate to job role and skill, we can start looking at the sensitivity of changing the staffing model, adding testers, adding designers, adding developers, and it all comes out of cycle time. Now, a lot of my consulting work involves around helping people understand what is the benefit of a decrease in cycle time. And the way I phrase it to management is, if you could reduce cycle time by 10%, what would that mean to your business, your company, and your cash flow? Now, one thing that happens very early is even with the simplest model, you very quickly learn that if you just look at a throughput over a year for a maintenance team where there is no easily, readily available revenue value of each feature or product that's going to be released, if you just look at the number of features that can move through a system over a period of time, I can change the samples of those cycle time inputs by 10% and then project that forward to see how many more of those features could actually go through over a single year. And it's not linear. And this is very important because if we can find 10% waste, 10% of the time something sitting in the queue that we could reduce, we can start getting 17% more work throughput through a system. And this sort of is very valuable information to defending against having lean and Kanban initiatives, or actually actively hunting down anywhere where you can actually reduce waste in a Kanban system. And often it's to defend against the, Troy, you have to cut staff by 10% because of a revenue decline. And it turns the conversation around, no, I have to increase staff by 50% to increase cash flow. And it's all based on being able to play around with these numbers. Now, if you do have good revenue projections and forecasts for a feature, and here is one that's very similar to one I did for real, I can actually calculate from the date that from a certain date, how much revenue will be lost over that period of delay. And I really actively sort of suggest that you start keeping, if there's one metric that you can keep around, it's the cost of delay per day for each of your projects, because it becomes a great bargaining chip inside the company and a unit of revenue, a currency, to help you prioritize work in a way which maximizes cash flow on the ground. So it's a way of tagging possible projects and features and stories to help you communicate to everyone else where one has a bigger impact on the bottom line than another. And you'll see quite a staggering increase in revenue, in cash flow, based on a 10% decrease in cycle time. And this isn't an invented number. This is actually, and I go through later some of the mathematics about how this occurs. And it will depend on your company's, your product's revenue process and cycles and so forth, and seasonality. But especially when seasonality is at play, the cost of delay benefit is massive. So much more massive than quibbling over whether to hire an extra contractor or two. And if you can get a handle on using cycle time to build these nice little quick projections, you too can actually go and have those great conversations about how to staff appropriately. So, current forecasting practices. I have to address this first, and you all have been to David Anderson's talks and seen online. There's a lot of work in development which isn't active touch time. There's a lot of time where, if you read any of Don Reinertson's books and Flow and his second book, he talks about that. There's things spend a lot more time blocked waiting in queues than they do actually actively being touched. How much more is up for debate. Now, I can easily defend from everything I've seen that the small section that are in red are actually hands-on development time. If we include the time that it was sitting in someone's brain before it even got prioritized to even being worked on, and the time that it sits waiting for maybe a waterfall or a batch release process, it's quite low. In fact, I regularly defend 15% would be the upper limit for most large organizations touch time. Now, if we were absolutely perfect, if we could nail every story point estimate to exact point in time, we would be making accurate 15% of the total time it took to get a story through. So I'm not fully in the no estimates camp about estimating story by story, but even if we were perfect at it, it influences 15% of the total cycle time of getting a story from beginning to end. So it may not be the best use of our time. It might be better off understanding and estimating how long things are going to wait in these queues and actually managing these queues and buffers than it would be having developers estimate. So I'm not no estimate camp for everything. I just think we're estimating the wrong things. And I think we need to start estimating the things which go wrong more than the things that may go right. And in doing so, we would increase the ability of our forecast to reflect reality, which is what we strive to do. How to get a date. So what we're trying to do with a forecast is take numerous uncertain inputs. Now, I have to say, like, there's very little certainty in software. You can't know up front exactly how long it's going to take to develop the feature. Otherwise, you know, you have completed it already, and you haven't. So what we're trying to do with a forecast is we're trying to find a way to combine uncertain inputs, the number of defects that are likely to happen, the amount of scope creep that's going to occur over a period of time, how fast staff will ramp up. Will we be able to hire the staff we need to actually do a certain set of features? So what we're trying to do with a forecast is we're trying to find ways to combine these uncertain inputs. And that's what we're trying to do with cycle time. Cycle time history is one input, but so is the amount of work that we need to do, and so is the number of staff. So the way you combine uncertain inputs, or one tool you use, is something called Monte Carlo simulation. And it's a class of algorithm which just takes samples from history and combines them mathematically. And you have to do a more sophisticated process than just a mathematical operator, because the different inputs have different scale and units of measure, and some of them may even be ordinal. So you can't just go and sum or use an average of all the values and get a reliable result. If we just say tossing two die, for instance, there's two standard six-sided die. There's only two combinations which would add up to 2. There's one combination which would add up to 2, and one combination which will add up to 12. But there's 7 combinations which would sort of add up to 7 in the middle, because you got 3 and 4, 4 and 3, you got 5 and 2, you got many different combinations, and that's what happens when we start combining uncertain inputs together. So in our software we talked about historical cycle time. You might have a set of historical samples. You might have to go and estimate those in using expert judgment. I know Douglas Hubbard's talking here, and you need to go to his talk to understand how to get people to improve their way of coming up with those expert judgment inputs. But it's still uncertain at the end of the day. You're going to end up with a range. You're not going to end up with an exact number as an input. Planned resources, speculation again. You know what you have on paper. You just don't know what you're really going to have. So if you're trying to forecast a date, you need to forecast a range of scenarios about staff. The work, of course it's going to change. It's going to change fairly often, and it should for a healthy company. It should change fairly often. You should give the business the opportunity to swap out feature 2 for feature 3 based on some market pressure or based on new information that someone has about whether it will be a market winner. Uncertainty again. How much scope creep is there going to be? Yes, we try and avoid it, and we try and look angry when it gets thrust upon us, but it's going to happen. So it's another uncertain input that you need to combine into the models. Defects. They happen at a certain rate, and they take a certain amount of work to fix, and it's going to change over different phases of the project. The defects you get at the start of a project and the end of the project will be different. So I'm not trying to paint a picture of this as an impossible model to forecast. This is actually probably simpler than forecasting the weather, except with the weather, we have historical samples going back 50 years, and we roughly think that it's going to follow a finite number of cycles. But the same process happens, and over time you too will get that historical data about how accurate your models were and be able to adjust them accordingly. You just got to make a start, and this is what this presentation is trying to help you do. Make a start at being able to model and forecast. Now, we're not alone here. We've been talking about this for a few years. This is starting to be built into software products. So I know the sort of Lean Kit Kanban is going to come up with that feature here. So Digite, there's a Monte Carlo challenge today at 2 p.m, I believe. You should come along, because what these companies are doing is they're on the leading edge of actually saying, taking your historical cycle time data, your defect occurrence rates, and your scope creep and your feature backlog, and doing this model for you behind the scenes and giving you a result. So you're not going to, you might be able to avoid doing it yourself now, but the tools that you're working with are going to be doing it in the future. So it's good to start now to understand what they're doing so you know how reliable they're going to be. Now someone says, but Troy, we've got cycle time history, can't we just take the average and project it out? And absolutely you can do that. So if you had a set of cycle times and you took the either the median or the mean, and you sort of just hypothetically said to finish 10 stories with one person, we're just going to take the mean and multiply it by 10. So if the mean was 67 days, doing 10 stories, it would take 670 days, and that's all I did in this slide. What I also did, though, was I used a real company's historical data set of cycle time. And I did a Monte Carlo forecast using the same process. So I took 10 samples from their history, summed them together, 10 samples, summed them together, 10 samples, summed them together. And when you do that, you end up with a range of results, not an individual result. And if we were to go on the record and promise that we were going to use the average cycle time projected, 50% of the possible outcomes were beyond that date. Now, we've lost a bit of industry knowledge or history. There was a very good reason why doubling the estimate you heard was used historically in the 70s. It's a way of going from average to a more likely realistic value. We missed the step in the formula which didn't start at 0, it started from the minimum. It should be mean minus minimum times 2, but we just doubled it. If we did that, we would be more likely out around the high end. So so when you hear people doubling, it's not actually mathematically incorrect all the time if you're going to use the mean. It's a great double check. But with Monte Carlo simulation, we can actually start shifting where we give the answer to a much more confident level. We can say 85% of the time through my model, we finished in 793 days. 95% of the time we finished 851 days. Now, if it was critical, if someone's life was in jeopardy if you didn't make the release, you would use a higher likelihood. But as you are all expert managers going to conferences and keeping your education up to date, I think you can probably manage 15% uncertainty in your day-to-day work. But isn't it good knowing where you are on this curve? And that's why I use Monte Carlo forecasting as the tool of choice, because it gives me this range. Anything else as a straight static formula would just give me one answer again, and I would be a bit unsure about certainty. So I just described how I did that. The Monte Carlo forecasting, it's simply you have a set of cycle time histories. Who remembers histograms from school? How often a value occurred is how high the bar is. The value that occurred, or the bucket that it's in, the range that it's in, is across the x-axis. That's a histogram. You're going to see a lot of those. I'm sorry. It's just too good to not show. But what we do is, in a sampling, in a Monte Carlo sampling algorithm, is we take, if we were forecasting 10 stories or 10 features, we would take 10 random samples following this pattern. So there would be a much more likely chance for around 20, 30 days than around 90 or 100 days, but not a 0 chance, because historically it has occurred. And then we would sum them together. So if we do that many, many times, we get 295 the first time, 410 the second time, 187 the third time. You're starting to see we're building up a range. Now, draw your attention to the bottom right-hand corner. As we do that, if we do just 25 samples, we get a very ragged result histogram about how often those values occurred. But as I do more and more cycles, you'll start seeing it's taking a more predictable shape. And that's the general process that we're using to build those, the result histograms that you saw, which allows us to go on the record about how certain we are of a certain feature, a certain likelihood. Anyone got any questions so far? All right. So this is, I left a slide out. Of course, being a developer thrust into management about 10 years ago, I wrote a software tool to do the forecasting for me. And it's gone through some evolutions over the years. This is the latest evolution. If you go to bit.ly/agilesim, everything in this presentation, all the proofs that I do, all the samples I do are actually on there for you to download. So you can actually see this for yourself. But the thing which has changed recently is that I've been putting a lot more work in cost of delay in my forecast. So what you're seeing down here is how likely a certain date is in completion. It's moving that bar across the histogram about how certain I am, and how many simulated outcomes actually occurred on or before that date. The cost, which is just, there's a formula in there. You can put in a formula about the number of people, amount of time. You can do some simple math to do that. We do it for you. And cost of delay. And cost of delay is a very important metric, because if we just say we want to bring this date in and add a developer, it's going to increase the development costs. If we can't articulate what the actual benefit is of going to market earlier in how much more revenue we're going to earn or how much more revenue we're going to protect, then we're never going to get staff approved through that process. You need to start thinking about how to measure cost of delay to do that. Because what happens is if we just look at three variables here, you've got a number of staff, you've got development cost and cost of delay. If I change the date, yes, staff go up, yes, development cost goes up, but cost of delay goes down because we're shipping earlier, so we're going to make more revenue. Now, it's not a linear response in most companies. Again, it will depend on your product lifecycle profits and how you're going to earn that money. But it is about understanding and able to articulate the cost of delay is a very important factor in managing projects and prioritizing.
Last question about that.
Question from the front.
I don't know if we need the mic, but for calculating the cost of delay, what granularity is appropriate or particularly too small for calculating cost of delay?
So the question was, is there a lower limit where calculating the cost of delay defeats the purpose? There's no benefit. It's going to be so small that it's not going to sway anyone's decision. Is that?
Not just for decision making, but also for the practicality of it.
Practicality. So it's how practical is it to calculate cost of delay? Yes, it is very difficult to get people to go on the record about value of each feature by feature or product by product. Some are easier than others, so it really depends on your market. I go through a few here that, it's the sum of the revenue that you miss, so it's new revenue that product would generate or how much revenue you would protect. Sometimes it's easier for people to say, it's really easy if you're going live for a Easter sale and you need to have a website change for hotel offers 3 months beforehand to go online, or you're trying to get ready to sell out tickets for a certain concert, because you know that if you miss a date, cost of delay is astronomical. It defeats doing the project at all. It's almost infinite on project basis. For each feature, it is hard to get people to go on the record to put monetary values on it. It's not impossible, and it will be different for every type of feature and company that you're in. Now, I'm going to answer that question by also saying that, and often missed, and this is missed in even books which spell out cost of delay as a great measure, we often forget to also, if you've got feature 1, which has almost no revenue generating capacity, but you can't do feature 2, which has a lot of revenue generating capacity, but you can't do that until you finish feature 1, then the cost of delay for feature 1 should be the cost of delay for feature 2 plus feature 1. And we often forget to project forward the cost of delay of dependencies. And that's why we find getting refactoring projects approved so difficult, or performance improvement projects so difficult. We often forget to project through the revenue. So to answer your question, I would be finding a project that is in jeopardy that is easy to measure its revenue deficiency, its cost of delay, and find out what projects and what features are actually dependencies for it. But I have a whole tutorial on Thursday, and this is half a day subject, trying to talk about how to get cost of delay calculated. And to be honest, it's a work in progress. I think it's hard, and a few people are good at it. Don Reinhardson's probably the leading expert on it. Costofdelay.com or .org. There's a guy who actually has the domain name, and he's got some great ideas about how to quickly generate cost of delay. So I can send you my references and resources, but it's not easy for all products, and it's really easy for some. But just key takeaway, remember to sum up the cost of delay of your other projects. Also remember that I see there's some online tools and frameworks which try and build in cost of delay and give you a weighted shortest job first scheduling, which is a way of sort of saying we want to we want to balance out getting short jobs and high cost of delay jobs together. They do a very poor job of incorporating risk into their model. What risk really is how uncertain, how wide that result curve is. And I think if you're using Monte Carlo and cycle time, then you are actually incorporating an element of risk. Second thing you need to justify and make sure is that you're there's some things that go wrong, like performance issues, which will increase the amount of work that you need to do to complete. So there's certain risks which have contingent backlog, and they're especially important for you to model and have a track on. So if we go live and we can't maintain a certain performance level, we're going to have to go back and add more indexing servers or change the way we write our code. Those delays are normally far bigger than any variability in story size, because they could double the backlog size overnight. So risk. But I'm not on the risk track this year. I was on the risk track last year. So that's happening later. So again, when you give a forecast, don't give just one forecast. Up front, give your executives the benefit of actually understanding what they can do about bringing a date in. And understand that the cost of delay. Let them make the decision. Don't just give them a date and start bargaining and negotiating what staff you need, what features are going to make it and not make it. Make sure they realize there's another very big lever they can pull here about investment, and give them options of staff. And this is probably the key differentiator when you have conversations around presenting a forecast and then showing what they can do about it at the same time. It's a much more balanced conversation than IT is just the largest cost budget item. We need to turn it into being a revenue item. We do that by tracking cost of delay, and then we do that by showing them that we have a way of forecasting what the improvement would be if we actually increased resources and revenue. And this is how I present my forecasts at an executive level, because there's only a few things that they're interested in and the rest of it is noise. One is I give them the features that they said were in priority order. I give them a date with a couple of staffing levels, a couple of staffing options. In other words, this is your current team. You said you wanted to cut my budget. This is what it would be if you cut all my contractors. It's a very common sort of ask. What if I got rid of the contractors? Well, the difference is about 2 months at the end of feature 7, or about 1 month at the beginning. So are you willing to, is it worth the investment? Then I also give them a staff hiring order, that if you don't like that date, then this is the order that you need to start hiring staff. Because that's the next question that's going to come off their lips. That's unacceptable. That's great. But if I also had this slide as the next slide saying, I'm glad you said that, this is what you can do about it, it's a much easier conversation to have, and it's not disjointed. It's not go away and make the team re-estimate is what I normally heard. That's not a valid answer. I'm confident my model is accurate. You can't just say it's inaccurate. So this is what you need to do. You need to be firm on that. So to do the outer forecasting, which we did before, just on those dates, about what dates we would actually go live for what feature for one staffing model, we just really need the total cycle time, or around wherever you choose to measure it from. You just got to be consistent, right? If you start measuring from the time that a story went into the backlog to the time it actually went into the release window, when you forecast how long it takes to do 10 features with 3 parallel groups, it's the time it's going to take 3 features and 10 parallel groups to go from this point to this point. So you've got to be careful and accurate about where you measure cycle time and lead time start and finish to. You also need, if you want to do this staffing analysis, if you want to start sort of portraying out the scenarios about what if I increase the development or test, you need to start, you can start measuring the intermediate cycle times. Now in Kanban, in digital Kanban tools, this is automatic. You actually get samples from as it moves in and out of the different columns. So that's what we're trying to do when we forecast the staff ratios. Oh, thanks, I can stop looking at my watch. What we're really doing is we're simulating what ratio works between development and test for a certain type of work. Now, here's something to be wary of that I found through practice, is that different types of work in the backlog emphasize different skills. So even in development, you'll have some skills which are UI-heavy, JavaScript, CSS-style stories, and you'll have some back-end stories. So sometimes when you're projecting staff, it is important to realize that you might even want to do a separate cycle time for the different types of work that you have and be able to show that a certain upcoming project will emphasize a certain set of skills rather than just be generic. So you have all these options for where you're going to measure cycle time from and to. And when we do that, the change is that we actually simulate the planned resources and effort. We divide it into 3 different segments, and then we work out whether it goes through a serial flow, or how much parallel work there is, or how much skipping there is. Some design stories may skip test altogether because they're just their UI work. Not that they're not going to be tested before release, but they're just not tested at that time. So it's about what we do is we forecast with the staff we know. And now we start doing what-if experiments. We increase the number of design staff, and then we do a forecast. Then we reset it back to what it was, and then we increase the development staff, and we do a forecast. And then we reset it back, and then we do test. Increase that by 1, and do a forecast. The one that made the biggest delta in release date is the staff that you should potentially think about hiring next. So you write that down, then you set the staff to what that level is, and then you do it again and again and again and again and again. And you'll get a big decrease in forecast date to begin with, and then it will start flattening out and start to cycle. So then realize that your option is that you need to add them in groups of 3 or groups of 4. A set of design development testers go in a batch. But I often find that by every team I've initially gone and modeled, there's always a 20 to 30% decrease I can do with 1 or 2 staff changes. And the problem was that everyone knew what those staff changes were, but they didn't have the data and the cost of delay value to defend and back it up. So all I'm preaching to the converted here is that by very simple models, you can get that number of that cost of delay and what the impact is of a date by changing staff. And you can use that to get your teams more balanced, so that you're not working overtime and hours. But what happens is it's 1 person or 2 people with a very specific skill working overtime and long hours, and then they leave your company, and they were important for a reason. They were your constraint already. So if they leave, that risk for the company is huge. So don't forget to quantify that value to the company. If we lose one of our key staff who is causing this sensitivity impact on staff, that is a huge risk for the company, which is why we don't want to run companies in such a poor fashion. So this is some new work, and this is the first time I'm actually going on record and video saying this, and it's taken me a couple of years to work out. It's that I always find cycle time follows a certain distribution shape, and it's normally thought of as being log normal, which is one of the candidates that it could be. And it could be one of maybe 3 or 4 others. Now, why is this important? Because if we can know the mechanics why cycle time follows a certain shape, we don't need as many samples to deduce what the shape might actually end up being to make our forecast more accurate. In other words, this is, I think, about 800 samples which I got from a real project. But if I didn't have that, or if the next project was remarkably different in style and work and skill emphasis than the previous one, knowing the reason why cycle time through a dev team will follow a certain shape means that I potentially could make some better guesses on what that shape will be with much fewer samples. So to me, it's very important to know. And I use it before I take a contract. If I grab their cycle time data and I do a histogram and it doesn't match roughly one of these shapes, I don't take the contract because I know the data hasn't been captured correctly or I've been lied to, and that's not a contract I want to get involved in. So there's log normal is the orange one here that has that very tall peak and a very it's got a concave on-ramp side. I actually That's my least favorite. That's the one I have seen least through looking at real data. Even though it would seem natural, it just had some, I don't know, 5 minutes to go. I'll do it anyway. Go big or go home. It's interesting though, you think that a lot of these distribution shapes are found through mathematics, and it's actually not quite true. In fact, the most popular, even the normal distribution, was found through measurement variance. Mechanical measuring of items and samples had a value and a variance. You get a normal distribution when you sum together a value repetitively that has a variance. So if it's 2 plus or minus 1, you will end up with if you did that measurement multiple times, you end up with a bell curve with the median and the mean on 1 with a variance of 1 either side of it. It'll be a bell curve. I'm not going to do the math on stage as to where that would be, but it's going to be the shape of a bell curve. Now the Weibull distribution is this green one here. Now it was found in a paper that was back, I think, in the 1940s, where the authors, the conclusion was, I hope you find this curve useful. It was very understated when it was released. But he found that by measuring the size of the dust on the floor from a grinding wheel in a mechanical factory, it followed the Weibull distribution. Well, it turns out that's not just all that follows that. Ball bearing wear, a lot of everything to do with the replacement time periods in mechanical wear tends to follow the Weibull distribution, as does the size of diameter of trees in a normal untouched forest. These curves were often found before they were explained why that curve fitted the mechanical process. So I've been trying to do the same thing with cycle time. I've been trying to understand why is cycle time following what I think is more of a Weibull distribution of a very particular size and shape, not log normal. And so I set about, can I do my own model and forecast to actually get this shape to occur? And I think I have. So the first one we talked about was if we just had a normal project and it was we had to do a finite amount of work and that work had a bit of variance in it, we would end up with roughly a normal distribution. Now I did 1,000 samples. It would be more normal if my random number generator was better and if I did more samples. But it's roughly normal. But what happens in software is we have the work we know we have to do and an unknown number of things that can go wrong. And as we start adding those, of course, if there's a 25% chance of one possible delay, something sitting in a queue, we would end up with 25% of the samples being the base work plus the work that we had to do with the delay. Now, if there were 2 delays, again, it was the base work plus 2 chances of 25% that we were going to be delayed. We would start seeing a smaller tail out there and a bigger tail. 3, we start seeing a bit more. 4, well, now there's more combinations which can start adding up to, well, because there's only 25% chance of each of those delays. Some of them only happen 1 or 2 times, which is why we've got a lump back over here on before the ones which are most often, just like rolling to die again, we got sample. And then 5 delays. Now, in software, I find this matches, and I can understand the mechanics of why that may occur. I think it's actually what does occur when I look at the timeline of what happens in real cycle time delay. It does occur. I think that it actually it matches the model. And so any time that you have a process where you have a base amount of work plus n number of things that could go wrong to delay you, which have a probability less than 100%, you're going to turn out to being this Weibull style curve. And through my work, I'm pretty certain that it falls into these rough parameters, which is a bit math and geeky, but I wanted to put it out there in the public to try and get some feedback as to what you see with yours. So that's it. That's it from me. Thank you for putting up with some math in the morning. Sorry, there's questions. Sorry?